For roughly 3.8 billion years, evolution has been running the longest experiment in Earth's history. Every generation has been tested. So here's the paradox. If evolution is so good at eliminating bad designs, why are you aging? Why do your muscles weaken, your skin wrinkle, your memory fade, and your organs slowly fail? Shouldn't billions of years have been enough time to fix something that eventually happens to almost every human being? The answer begins with a misunderstanding. People often imagine evolution as a perfectionist, like an engineer endlessly improving a blueprint until every flaw disappears. But evolution doesn't work like that. Imagine a theater production. The audience only watches the first act because that's when the competition is judged. The actors perform brilliantly for 40 minutes. The lights are perfect. The costumes flawless. The applause decides the winner. What happens in the second act? Nobody is watching anymore. The props can wobble. The paint can peel. The costumes can unravel. It doesn't change who already won the contest. Your body is surprisingly similar. Evolution cares intensely about the opening act of your life. After that, the audience slowly leaves. That strange rule shaped everything that followed. For most of human evolution, reaching old age was uncommon. Not impossible, but uncommon. Around 2 million years ago, as early members of the genus Homo evolved larger brains, longer childhoods, and more complex social lives, they also invested heavily in growing, learning, and reproducing. Building a body capable of surviving long enough to raise children required enormous biological resources. But maintaining that same body forever would require even more. Every day, your DNA is damaged by sunlight, oxygen, chemicals, and ordinary metabolism. Proteins misfold. Cells accumulate tiny errors. Telomeres shorten with repeated cell divisions. Your body constantly repairs this damage, but never perfectly. Why? Because perfect maintenance is expensive. Every calorie spent repairing today's cells is a calorie not spent growing, fighting infection, finding food, or producing offspring. Evolution had to make a budget. And that brings us to one of the most important ideas in biology. In 1977, evolutionary biologist Thomas Kirkwood proposed the Disposable Soma Theory. The name sounds harsh because it is. Soma simply means the body, the physical tissues that carry your genes. Kirkwood argued that evolution doesn't maximize longevity. It maximizes reproductive success. If resources are limited, natural selection should favor investing just enough in maintaining the body to survive through reproduction, not forever afterward. Your body isn't neglected because evolution forgot about it. It's maintained only as long as maintaining it improves the chances that your genes reach the next generation. Imagine two sisters. Olivia's body spends enormous energy repairing every microscopic defect. Her cells remain pristine for decades. She ages slowly. Emma's body performs good enough repairs. She has slightly more cellular damage over time, but she reaches adulthood earlier and can devote more energy to reproduction. Now imagine this repeating over thousands of generations in an environment where food is scarce and many individuals die from accidents, infections, or predators before old age. Which strategy spreads more genes? Ironically, it may not be Olivia's, because evolution rewards reproduction, not perfect preservation. Nature offers astonishing evidence that this trade-off is real. The naked mole rat, for example, lives for more than 30 years despite being the size of a mouse, showing unusually effective cellular maintenance and remarkable resistance to cancer. Meanwhile, many mouse species reproduce rapidly but age quickly, often living only 2 or 3 years in the wild. Different species solve the maintenance budget differently because they face different evolutionary pressures. Humans landed somewhere in between. But aging doesn't simply mean wrinkles. The consequences become stranger the deeper you look. As damaged cells accumulate, some stop dividing but refuse to die. These are called senescent cells. Instead of quietly disappearing, they release inflammatory chemicals that affect neighboring tissues. Scientists sometimes call this chronic, low-grade inflammation inflammaging. Your immune system also changes. It becomes less effective at fighting new infections while becoming more prone to chronic inflammation. One process feeds another. Repair slows, damage rises, inflammation increases, repair slows even more. Worldwide, the World Health Organization estimates that by 2050, the number of people aged 60 years and older will reach about 2.1 billion, more than double the figure from 2020. Age-related diseases are becoming one of humanity's greatest medical challenges, not because evolution failed, but because more people now survive long enough to experience the later chapters evolution barely optimized. Here's the uncomfortable part. Natural selection mostly sees traits that influence survival and reproduction before or during the years when individuals are likely to produce offspring. For ancestral humans, that critical window was largely the first few decades of life. Once most reproduction had already occurred, the force of natural selection weakened dramatically. Damage appearing at 60, 70, or 80 years old barely changed whether those genes had already been passed on. From evolution's perspective, the audience had already left the theater. For decades, another famous explanation tried to capture this same idea. George C. Williams proposed the theory of antagonistic pleiotropy in 1957. The idea was that some genes provide powerful benefits early in life but harmful effects later, and natural selection keeps them because the early advantage outweighs the late cost. Evidence has supported this mechanism for some genes, but modern research suggests aging is probably not driven by a single explanation. Scientists increasingly view aging as the product of several overlapping processes: disposable maintenance, antagonistic pleiotropy, mutation accumulation described by Peter Medawer, cellular senescence, mitochondrial dysfunction, and many others interacting together. In other words, there probably isn't one aging program hidden inside your DNA. There are many compromises layered on top of one another across millions of years. That changes how you should see your own body. You weren't built to last forever. You were built to last long enough. Everything after that became increasingly invisible to natural selection. And yet something remarkable happened. Humans changed the rules. Medicine reduced infections. Agriculture stabilized food supplies. Technology protected us from predators and starvation. Today, millions of people routinely live decades beyond the period where evolution applied its strongest pressure. We're spending more time in the second act than almost any of our ancestors ever did. So now return to that theater. The curtains are still open. The actors are still performing. But the competition ended long ago. The peeling paint, the worn costumes, the flickering lights, they aren't signs that the play was badly written. They're signs that it was never judged beyond the opening act. And perhaps the strangest truth of all is this: you are living in the part of the performance that evolution was never really watching.